So today we are going to discuss a topic, two topics. First one is how you can combine different languages and use the features of one language in another language. The topic is generally referred to as mixed language programming. And in this course, we will be looking at how to combine Fortran with Python. So in my course folder, the Git Compute course public, there is a folder called F2Py, and the examples I'm doing here is available there if you want to do them standalone. So how do you integrate Fortran and Python? So Fortran and Python are quite different languages in many senses. So Fortran is a compiled language that compiles source code to machine code. Python is an interpreted language that compiles every line in your code to machine code every time. So it's not compiled in one go. It's kind of interactive. Python has the ability to implement functionality in something called extension modules. And extension modules are a way of integrating compiled code into Python. And most of the functionality in Python is actually implemented in other languages. So the runtime library, several of the routines there is implemented in C. And to implement these extension modules, you need to use something called, you call the Python API, and compile your C code in a special way so that they can be loaded by Python. When you have compiled these modules, they can be used just like any other module in Python. There is no difference. You can't even see that there is a difference. The only thing is that probably the speed will be higher when you run them. However, implemented Python extensions are really hard. Really hard. It's complicated. So in this code here I'm showing on the screen now, shows a source code for a simple extension module summing two objects. So you can see here that there is a lot of special declarations here, Py objects. Those are data structure that describe a Python variable reference. And here is the C code of two variables that I want to sum together. You have to parse the arguments here to retrieve the A and B. And here I do the computation in C. And then I return the results by calling a function build value D and setting C here to this value here. So this will return a Python object or Python variable reference. Then I also have to specify which methods to export from this module. And that is done by defining this data structure here. So I want to export a sum function. There is also some help information here as well, and the variable as well. And then I have to initialize the module, to kind of, and also this module is called C extension here. And then the module functions that go into the module is here, and this is the module documentation here as well. So this source code you compile with a C compiler to generate. On Windows, it will be called a dynamic link library. It will have the PyD extension in Python. On Linux or Mac, they will have the .so for shared object extension. And so there are binary modules like executable, but they don't have a main function. And then you load those modules into Python. And they will behave just like normal Python modules. So, however, there is an easy way for Fortran. There is a tool that is available in the Anaconda distribution called F2Py, which what that tool does, it translates the Fortran code and generates the necessary extension code, source code in C to build an extension module. It can automatically handle NumPy arrays as Fortran arrays. It's a command line tool, so it works by issuing a command on a command prompt either in Windows or on Linux or Mac. Also, a final point here is that it's kind of hard to debug. So before doing your implementing your extension module, make sure that your code is works as normal Fortran code. Because if you don't, you will have you don't get clear error messages from F2Py regarding your if there's something wrong in your Fortran code. So it's good that you compile and debug your code first, then export. Then you only have to look at the errors from F2Py. We'll start with a simple example. So I have a subroutine here, 3 parameters. 2 of them are input arguments, and the third one is an output argument. And we will compute C equals A plus B. So to convert this to a Fortran extension module, you issue the F2Py command. Please note that the exclamation mark here is just so that I can, from my notebook here, can execute this in the environment. So on a command prompt, you just type F2Py. So the first argument here, M here, that is the module name for the module you want to create. -C here is to compile, and this is the Fortran source code that you want to compile. So let's see here, if I run this, you can see here that there's a lot of output from the F2Py command, but you can see here that the first step it does is to analyze the source code, reading Fortran code, post-processing, building modules here, and this is you can see here that it generates here C code, and in the final steps it will also build the C code into a module. So if we list, if you look now in the directory here, it generated this file. On Windows, it will only generate simple.pyd, but on Linux, it will also add this extension here, CPython 37M, and that is because the Python binary interface between different versions are different. This is to be certain that this will only be loaded by, in this case, a 3.7 Python compiler, and that is a 64-bit module here, compiled for Linux GNU. So you don't have to do anything special to use this module. You don't have to specify this long thing here. You can just import it as simple. So let's see what happens when we now execute this in Python. So what we can do now is just like we import normal module in Python, we import simple. If we run this, you can see here that it generates documentation as well. So in this case, it said that this module is simple, it's auto-generated with F2Py. It contains one function here, C equals to simple A, comma B. We can also print the documentation for the simple function. So you can see here it generates documentation for the imported function as well. So simple doc here has parameters A, B, and returns a float. And also see here that return values are moved to the left side or equal sign, so it becomes a function. If you have return value, the subroutine in Fortran will become a function in Python, because Python doesn't return from the input arguments. So let's test this out, see how it works. So we define our variables in Python here, and we call our function, and hopefully it should return 84. So it seemed to work. And you can see also here that we had in our Fortran code, let's see if we can go back here. We had floating point. So the conversion is handled automatically as well. You don't have to think too much about that. But it returns a floating point. So now we move on to something a bit more complicated. So in this case, we will use compile a Fortran code for multiplying matrices. So this is, of course, already built into NumPy, so we don't have to do this, but it's just for illustrating use of arrays in Fortran, in F2Py. So in this case, we have matrix multiply. We have A, comma, R, comma, S. So we will have to pass the sizes of the arrays over, B, T, and C. And we declare them in our Fortran code like intent in, and out. And the reason I use intent in here is that this is something that is used by F2Py to figure out how it will generate a function in a way that you can use it from Python. Then I do the implementation in Fortran here, which is just calling matmul of A and B. Then we compile it. So I call this module ARR1, and I compile ARR1 F90. So now let's first, it's always a good idea to look at the generated documentation here. So every module has this doc here variable that you can call up. It's a string that contains the documentation that F2Py generated. So in this case, you can see here that I have R1 auto-generated with F2Py, and it provides a function called matrix multiply. And you can see here that it has also documentation for how to call this here. And we also look at the actual function documentation. So you can see here that it generated a function called matrix multiply. It returns another array here, C, and it has input parameter A, comma, B. And one thing you can see here that the R, S, and T parameters are in a bracket. And that means that they are optional. And what F2Py does, it can see if the parameter is used to declare the arrays, the size of the array, that information can already be passed along from a NumPy array. So you don't have to give those parameters explicitly. It's passed along. So now the function actually becomes very simple. So you can just call matrix multiply with two NumPy arrays, A and B. You don't have to specify any of the size parameters. You can also see that it's an array of float with the sizes R, comma, S, with bounds S, comma, T. And it returns a rank 2 array of floating point. So let's try this out in Python as well. So of course we import our NumPy. Here's a note that we need to look at, and that is Fortran stores its arrays column-wise. C does it row-wise. And that to be able to call a Fortran routine correctly with the right ordering, we need to create NumPy arrays specifically with that ordering. And there is an attribute you can specify, an additional option in when you create new arrays in NumPy, and that is called the order parameter here. So order here tells NumPy to allocate this array column-wise, or in Fortran format, F. So I create A, B, and C here in Fortran format. Then also I will also want to illustrate something here that you need to think about when using NumPy arrays. So F2Py is extremely good at converting to Fortran. So it will kind of change the ordering of things if it needs to. So there will be copies made. So in this case here, we'll run this and see what happens. So you can see I created C here in NumPy, and when I do C equals to array here, it will. You can see that the ID of C is different. That means that C was created by the matrix multiply function. So this will be a copy. So you can see here that the C here will be overwritten and not used. So you could have actually commented this line out and only allocated A and B. So let's do that. Just put a bracket here and we'll run that again. And now it's okay. I will skip that here. It's not. So you can run this without actually allocating the left side of the function. So if you want to avoid this, if you want to the function in Fortran to actually work on the arrays that you have defined to avoid unnecessary copying, that can be done as well. So in this second example here, we give A and B just like before here. This is exactly the same, but instead of having just out here in the final declaration, we provide in out. And by doing this, we will keep the array in the call, so the function call. It will not be moved to the left side to the equal sign. It will be a variable that comes in. And because arrays in NumPy can be modified in functions, you can do this. It's not possible with scalar variables, as I showed before. Then you have to have them on the left side to be able to return. But an array can be modified inside a Fortran function. So let's compile this with F2Py. And we look at the documentation again. You can see here now there is no left side here. So this is a matrix multiply 2, A, B, and C, and the shapes here. So the C is now kept in the arguments to the subroutine. And if we look at the documentation of the actual function, you see here you don't have to specify any of the size parameters. And see here in out rank to array. So difference is here that this is input output. That means that it will be modified inside the subroutine. Now, if we look at the Python code again, we need to declare all of 3 arguments now because it will be passed over in the subroutine. And now you can see here that ID of C. So, and also what comes out is still the same array, but now C actually contains the multiplication, the result of multiplication. So we declared C here in this part, and this is the C that has been computed inside of the Fortran function. Also, in the next example here, we will look at, you can actually import, or F2Py can convert entire modules as well into Python modules. And when you do that, it will create a module within the module. So you have one module that is the F2Py generated module name, and inside that, every module you define in a Fortran source module will be a sub-module to that one. So I will illustrate here. So I have a module matrix here that contains both our previous functions here, matrix multiply and matrix multiply 2. And now I compile F2Py here. My outer module is also matrix. And if we continue down here, look at the documentation, import matrix, you will see here that I have this module matrix auto-generated. So it has a matrix module here inside the outer module matrix. And then if we look at the matrix of it, contains the matrix multiply function and also the matrix multiply 2 function. And sometimes if you have modules in your source code in Fortran, it's sometimes it's better to use Fortran matrix import star. Then it will import all the modules inside that outer module into your code. So in this case here, if I do this instead, I can call matrix multiply here. So now I don't have to do matrix to access the matrix multiply 2 function here. So this is what I wanted to show how to do mixed language programming. F2Py is one of the tools. So if you're using Fortran, F2Py is I think this best tool. It does a lot of things automatically by reading the source code. So you don't have to modify your source code in any way using F2Py. And also, yeah, I mean, it's hard. I don't think there is a lot of others. There are some manual tools. So the alternative is actually use directly the C API that I showed you in the beginning. But that is not, it's very hard. And then you also have to think about how to call your Fortran routines from C. And if you are coding in C++, there are other alternatives. There's something called PyBind11, which is a tool to generate Python modules from your C++ source code. There is Swig, a simplified wrapper and interface generator, which can generate modules for different scripting languages from different source languages, specifically C. But F2Py, if you want to combine Fortran and Python, I think F2Py is the best choice. And it's also built into, if you install NumPy, it will come with that from the code here. And I think I will put also instruction on how to get this to work on Windows as well, because it's a bit complicated to get F2Py to work on Windows. It works out of the box on Linux and Mac, but Windows is a bit problematic. So the second part of this lecture will be about tools for modern Fortran development. So this is not so much programming, but how to how you build software in a more efficient way, and specifically then Fortran code. So maintaining Fortran code. So as I said before, when your project grows, compiling and adding and maintaining your code will become a larger effort. Perhaps you have requirements for building your code on multiple platforms. So not only Mac, but Linux and Windows. And shell scripts can be used for small projects, but they can't handle source dependency easily. And often they will require that you rebuild everything from scratch every time you run your scripts. And here there are some tools that can solve these problems. So we have two major ones that are used for building software, and it's called Make. And then there's also a tool called Cmake, which is a meta make. It makes it easier to create make files. If you don't have to generate them yourself. You use a more advanced language, which is easier to use to create make files themselves. So let's start with Make. So Make is a special software tool, command line tool, that builds software based on a set of rules. And it can automatically handle dependencies with source files, so that when you build something, if you change the source code file, it will only rebuild the required files depending on these rules. So if you have a large project and you change a single file, it will only rebuild that file and the final executable. It will keep all the other stuff that it built, so it's much more efficient. And if you have used Qt Creator already, you will have seen that it uses both Cmake and Make. And if you have multiple files in a Qmake project or Qt Creator project, it will automatically figure out what to rebuild. Oh, let's see here. There's something wrong with the share here. One moment. Okay, I will go back shortly here just to recap. Yeah, as I said before, so when a program gets larger, the time you need to actually maintain the project grows, and also building on if you want to build on different platforms, you need to support specific tool chains for different platforms by yourself. Scripting is something that many people use to solve this problem, but they can't handle source dependency. So usually you have to rebuild the entire stuff every time you run the shell script. And here, Cmake and Make can solve these problems. So Make is the first tool. It builds software from a set of rules. And it can handle dependency in source file by rebuilding only the files that have been changed. It's available on all platforms. Cmake is the most commonly used. Just an anecdote, Microsoft actually builds the entire Windows operating system using the Cmake tools. So it's used not only by the Linux community. It can be a bit non-intuitive in the beginning, so until you kind of understand how how you define the rules and how the execution of the rules work. So the basic syntax is the following. You have a target that is what you want to achieve, and that target can have dependencies. So before that can be built, some of the dependencies have to be fulfilled. And to achieve the target, you specify the commands that you need to execute to achieve this. And here comes the first odd thing with Make, is that it has to be indented just like Python, but it has to be indented by a tab character. So you have target, system command to achieve that target. So just to illustrate a simple example here. So this is a rule to build a GC file. So compressing a file. And to achieve this file, we have a dependency. We need the uncompressed file, myfile.txt. So that is the file we want to compress. To achieve this, we can use command line on Unix here. We can cat the file, myfile.txt, pipe it to gzip, and output myfile.gc. So the second part here is how to achieve the goal, myfile.gc. And myfile.gc will only work if myfile.txt is available. So that is the dependency. So I will see if I can show you this. Can you see a command line prompt now? Good. I have a make file here. Okay, I can't run this on my Windows machine. I will skip that one, but this will build a file, and here is that was a bit unprepared. Next one will work. So running this here, so in the rules in Make you will place in something called a make file. It can be any file name, but if you have if you place it in a file named make file with an uppercase M, it will automatically use that file. Otherwise, you have to specify with the -f which make file to use. So if I just type make on the command line prompt, you can see here that it will. So I can find. So you can see here that it will execute this part here, and that was the command I gave in the rule. And if you look at ls here, you can see that it created a myfile.gc file. Then the nice thing we make, if you do that again, it will detect that okay, myfile.gc is up to date. There is no need to do anything now because the GC file exists. And there is no modification to the myfile.txt. So what happens if I modify the text file? So touch is a command that will modify the update time of the file. So it will look to the system like somebody modified the file. Then I type make here, and you can see here that it executes the file again. The commands in the rule. And that is because make the text that's myfile.txt is newer than the GC file. And then it realized that now I have to actually build that file again because it's not up to date. So in this case, you see how you can apply this to source code. So if you look at how you build source code files, so building an executable requires you to compile source code to object files. I have shown you that in some slides when I did Fortran, and linking object files into an executable. And dependencies here are object files depend on the source code files, and executable depends on object files. So you can see already here we have a case for make. So we start with the first rule. So in this case, this is a Unix system here. So we have a myprog here. That is our main executable. It depends on myprog.o, which is object file. And to be able to achieve this, we have to compile it with myprog.o, output myprog. And then we have another rule here to generate myprog.o. And that depends on the source code file myprog.f90. And then we have jfortran -c myprog.f90. So this line here will generate the O file, and then myprog here will create executable from that O file. So let's see if I have this one in my examples folder here. So you can see here I have a make file here, and I can type, if I type this here, now this is a Windows machine, so it's a bit different commands here, but you have these things here, myprog.o, and then myprog.o to an executable. So if I run make here now, you can see here the first thing it did, it figures out which order it has to do the rules. So as myprog depends on myprog.o, it has to compile, convert them, execute the second rule first. So that is compile the source code file into an object file. And then finally, it creates the executable by linking them together using the O command. So if you look at, so on a Linux machine, the myprog.exe would be just myprog. In a Windows machine, it will add the exe file extension as well. But now it works. And also if I do, okay, I will do code. So if I just save this file again, close this window, and if I do make here now again, you will see here that it figured out that something has changed. And if I run this again, you can see here it will just link together here, those two. So this was first example. So what if you have multiple source code files? So in this case here, I have myprog, my module, so I have two source code files. One that is my module, and the second one is the main source code file. And to build this, you need, so you see myprog now depends on my module and myprog.o. To link them together, and then I have one rule for each O file. So in this case here, if I build this, first time it will build all the object files. The second time, if I just change, update my module source code file, you can see here that it only compiles the my module F90 next time. So it will not rebuild the myprog.f90. So let's see if we can do this here. This is the example here. I have a make file. This I do make. So it builds both the myprog and my module, and then I do code my module, and I just save this one again. Then I do make again. You see, it only rebuilt my module. If I run it again here, now it only links the modules together into the final executable here. So module dependencies. So in Fortran 90 and above, compilation order is important, because when you build a module, the Fortran compiler will generate information that is required for when that module should be used by another source code file. So module files must be built in. So if there's a module that is used by all other modules, it has to be built first. Then the next module has to be built, and then finally the main source code files. The source code file using these modules are built last. And we need to fix that in Make again. So here, this example here, I have 2 modules, and if I try to build them in this order here, you can see here that use truss here, so can't open module truss mod for reading. That means that the truss module hasn't been built yet. It built the main module first, and we need to fix that. So we have a dependency here between the modules, but luckily Make can solve that for us as well. So if you look at the Make file here again, module main.o, we can add module.truss.o as a dependency to the source code file build. Then it tells Make that the module truss.o must exist first before we build module main. And if we run this now, you can see here the first thing it builds is actually module truss, because module main requires module truss.o to exist. So that is a simple way of adding a dependency in your build. So as you see before, if you have a larger project, you would have a lot of make rules, and we can simplify a lot by specifying variables in Make. So Make is like a normal programming language. You can define variables, and that also variables can also mean that you can configure your Make script in a more easy way, make it more portable. So it works like bash variables. So assignment, you give a variable name equals to value, and you use that, you have a $sign parenthesis in the variable name. So the first thing we will simplify here is that we, instead of specifying our the compiler, we create a variable name FC for Fortran compiler. So then you can change your compiler, and you don't have to change it all over the place in your Fortran Makefile rules. We also give the compilation flags for Fortran using the F flags variable, and then also we change the executable. We define the executable name in an executable variable, and then you can use these variable declarations all over your Makefile rules. So executable depends on those modules, and instead of specifying the Fortran compiler, we just use $FC here for the Fortran compiler. You can also see here in the end here, I added a empty rule here, or a rule without dependency. And a rule without dependency you can execute by specifying make and giving it the name of that rule. So in this case, if I do make space clean, it will execute this one. And this is a good thing to have. For example, if you want to rebuild everything, you can do make clean. It will remove all the object files, mod files, and executable. So you can see here that rm.rf.star.o.star mod.executable. So it will remove all the binary files. then all the rules has to be rebuilt from the beginning. You can also have something called internal macros that can make even more generic makefiles. You can have a target of the current rule executed. You can have the name of all prerequisites and the name of the first prerequisite. So here you have the executable here, that's this rule here. So you have to build the first one here, that points on this one. And this one points to the name of the target here. So to build executable, I can, instead of having the name of the executable here, you can have $@ which is the target. And then you have $@ to point to the first and second dependencies here. So it will link those together here. So this will be these parts here. So the rule will be quite more shorter and more generic. You can also do, in this case here, I have my flags here. I have the first rule here. So this one points to this F90 file. And then output is the myprog.o here. So $@ here is the actual target name here. So you can see that the build rule, the commands building rule is completely generic now. So in larger projects, it can be difficult to maintain all these rules for single source code files. So there is something called suffix rules that can be described as recipes for converting source code suffixes to an object suffix. And then in this case, all the source code files, so you build a rule going from a source code file to an object file, and all the files in that directory will be, so you can plant all the source code files, all the object files. So in this case here, you have a suffix rule, so .f90.o, that means going from a source code file F90 to an object file requires this command. So this is means that all Make now knows how to go from an F90 file to .o in a generic way. So if you have any source code file and there's a dependency on that, the Make will know how to go from building an O file from an F90 file. Nowadays, I think this is a bit old, but which suffixes that are recognized can be added or modified using the .suffixes variable here. I think that most modern makes recognize that automatically. There's also something called wildcard expansions, which can be used to create lists of files. And you can also do path substitution using the path subs function. And that means that we can do even more generic make files. So for example, we can do, if we want to create a list of all the source code files in our directory, we can do F90 files, and then wildcard star F90. That means that the F90 files will be a list of all F90 files. Also note that we have to use : equals to do these kind of things. You can also, if we have all our F90 files, we can also create a list of all of object files. And then we can use this pattern substitution function. So here we say all the F90 files should be renamed to .o. And the input for that function is the F90 files list. So now we have a list of all our source code files. We have a list of all our object files, potential object files in this case. We haven't built anything yet. So here we can do even more easy makefile rules. So instead of actually explicitly stating our object files, we can use our objects list. So now we have executable depends on all these objects, $objects. And to link the binary together, we use our generic rule here. So this is the dependencies and this is the target. So now this rule has become completely generic. We don't have any explicit mentions of a source code file in our directory. Then there's also another way of achieving the same thing with instead of using this rules .f90.0, you can use pattern rules. And in this case, there's no need to use the .suffixes for additional files. And this is also the recommended way in Cmake to do this. And it achieves this with using the % operator the same way as for the wildcard functions. So in this case here, we use, here is so this part here, we have %.o, %.f90. So to get, to build a .o file, we need to, it depends on a .f90 file. And this is the rule to do this. We still keep our executable .objects here, but we add this suffix rule here. Or pattern rule, sorry, it was pattern rules, yeah. We still have to care about the dependency of the modules, but now we only have one line here. So the .module depends on myutils.o. So this is we still need that to solve the Fortran module dependency thing. But now it's a simple line that to tell Make that my module depends on myutils.o. There's no need to do anything else. So let's see if we can do this. This is the larger example I have here. Time with all the pattern rules. And actually, I had actually managed to make. So it builds the my pro.o and my utils is built before because there's a dependency here, and then my module.f90, my module.o. And if I do make again, it will only build a program. So if you don't want to mess with complicated make files, we can use another tool instead. So we will look at how to use something called Cmake instead. So Cmake is a cross-platform build system, and the difference between Cmake and Make is that Cmake will generate build files for different platforms of different flavors. So it can generate make files. It can generate project files for different development environments, Eclipse, Visual Studio, and Xcode. And it's actually a complete language. So you define your projects in a much more intuitive way than you do with the Make files. It will still provide the benefits of Make, because if you generate Make files, you have it will generate all the dependencies for you, and it will build only the things that have been modified. So here is an example of a Cmake file. The first line here is something that you need to add so that the Makefile tool will recognize which version you used which version of Make you used. And today I think it's 3.10 or something. Now this is 3.0, which is a bit old. Next comes the actual definition of your project. So the first thing you do is name your project. So project simple. So that is the name of the project. So it's not executable. So a project can contain both libraries and multiple executables. So it can handle a large project with different subsystems. To be able to use Fortran, we need to activate language support, enable language, and then you put Fortran with uppercase F. So then it will know that it will add stuff to recognize Fortran compilers. Finally, we need to specify our executable. That is done with the add executable command. And then you say the first parameter here is the name of the executable and the source code it requires to be built. So let's see if we can run this here. So instead of adding these instructions to a make file, you add them to a file called cmakelists.txt. And it has to be with uppercase and lowercase letters. It has to be exactly like that. Cmake looks for that file when you run it. So in this case here, you do Cmake dot here, and then you can see it does a lot of, it figures out which compilers to use, which is in the system, and then it will configure and create build files. So if you do an ls again, you can see here that there is a make file now. So Cmake generated a make file, and now you can just type make, and it will build your Fortran code. And that make file will contain all the dependency rules, everything required to build. So if you have a large project, it will only rebuild the files that you change. So it will use the benefits of make, but you don't have to bring out my PowerPoint slides or do the find out the documentation of make. You can just do this simpler language. However, this is not the way you should run Cmake. So running Cmake in the current source code directory is discouraged, because Cmake generates a lot of files when you run it. So the way you should run it is to create a build directory. So in your source code tree, you create a build directory, and you go into that directory, and then you type cmake dot instead of cmake dot. That will generate all the build files in this build directory. Nothing goes and touches anything of the source code directory. And that also enables you to, if you have something wrong with your build, you just remove that directory and recreate it. So you can see here it still works. It detects the C compiler and generates the make files in the build directory. So the make file will be in the build directory, but it will depend on the files in the source code tree outside that directory. You can also build both debug and release versions. So debug versions is binaries that is doesn't have, are not optimized, but have instructions for debugging added to it. And you set the Cmake build type variable to set what you want to build. So Cmake defines Cmake build type equals to release. That will compile an optimized version of your code. So one thing you can do here is you can have two build directories, one build release, one build debug, and you can build the release version in one of them and the debug version in the other one. So once you generate your make files, the debug will build the debug and the release will build the release version. You can also, many cases, you need to add libraries that your project depends upon, and you do that by using the target link libraries. So in this case, you specify that simple depends on the BLAS library and the M library, the math library, and Cmake tries to avoid using. So it tries to, on Windows, BLAS will be blas.lib. On a Linux machine, it will be libblas.something. So it can you can specify the name of the library, and it will add extension in Windows and add suffixes in Linux. In many cases, you need to do some kind of handle that by using if statements in your Cmake file, but it tries to be as neutral as possible when it comes to platforms. Conditional bills, so you can actually, as this is a language, you can do if statements in your make files or Cmake files. So for example, you can, if it's a Unix platform, you can do if Unix, then you can do stuff for Unix that is only done on that platform. There is also Linux, Apple, and Win32, which you can use as tests. And you can test a lot of things. You can define your own variables in your code as well. So here's an example here. If Unix, I will add my executables, but I will link with BLAS and M. If I'm running on Win32, which is Windows, I will link with BLAS32, for example, which is it's just made up here, but different library. And if it can't find the configuration, it will do not a supported configuration. So in this way, you can build specific, take into account the different platforms by checking which platform the Cmake file is running on. You can use variables, just like we did in make. So you can use set myvar and then assign a value. Then you use $sign curly brackets to access that variable. You can also use lists in the same way. So if you do set my list and then specify string with spaces, it will become a list. So here is I set a list with A, B, and C. So if I and then I can loop using for each, and you can see here that it will be A, B, and C that is in that list. You can also control optimization flags. So there are two variables, Cmake Fortran for the compiler, flags release. So those are the flags that are employed when you are building the release version, flags debug, the flags that are used for building the debug version. And the chosen Fortran compiler can be set using the Cmake Fortran compiler variable. These are usually if you don't say a compiler, it will figure out these variables automatically. But if you want to change, for example, the build flags explicitly, you can do that by changing these variables. So here are some example of this. So here you have if Fortran compiler is equal gfortran, I should employ certain flags. If not, I should, if it's a Intel compiler, use some other flags. So this way you can tailor the flags depending on the compiler that is used. It's also possible to generate, and this is one of the strengths of Cmake. So if you are a Windows developer or a Mac developer or an integrated development environment developer, you often want to use an IDE to compile your source code. And Cmake can actually generate the project files needed to generate the project files for each of these environments. So Visual Studio is supported, Eclipse is supported, NetBeans, Xcode, and more. And you can query which environments are supported by using the J command to select which one. I'm seeing if I can find. The J command is select the generator, and default is make files. So in this case here, you can see here that cmake.j eclipse cdt4 Unix make files. It will generate C project files and project files that you can open them in Eclipse. I will show you how that can be done as well. So if you just type cmake -j, it will list all the project files it can generate project files for. So you can see Visual Studio 17, 19, 20, 2015, all the Visual Studio versions. Ball and make files, and make files, which is Windows default make files. MSys, which is also Linux-based for running on Windows. Code blocks, Eclipse, Kate, Sublime Text. So let's see if we take this one here. We can do cmake dear Bill. Then I do cmake -j. So now it will generate Visual Studio 17 project files. I'm not sure it will find Fortran compiler here. Let's see. Of course, I don't have a Fortran compiler here. Let's see. this live here. Let's see if I can do this. So I will do add a file here, main.cpp, which I do. Cmake lists here. Project test, and then add executable simple main.cpp. So this is a very small one. I think it should work. So I will go back to my directory. Make their build, and then I will go into that directory, cmake -j. So now it worked. So you can see here that I got a lot of extra files here, and the important file here is the testing.sln. So if I do testing.sln, it will open the Visual Studio environment. If you have an Intel compiler or Fortran compiler installed on your Windows machine, it will work even with a Fortran example as well. But in this case, I don't have that. But you can see here that I have the main source code file is available to me here. So that's the benefits of Cmake. It can generate build files for Xcode, for Visual Studio, and for Eclipse automatically from the same source code file that you generate from the make files. So that was all I wanted to talk about today. So we have a seminar on Thursday, and I will put out some more information about make files and how to use that on Windows, and for Linux and Mac it should be quite the same. Okay, see you on Thursday then.